Hello, we are Group 5 and our topic for discussion today is condition monitoring of equipment in nuclear power plants. Nuclear energy is one of the clean and cost-effective source of energy. However, events such as Three Mile Island nuclear plant in 1979, which barely escaped the disaster, the Chernobyl explosion of 1986, which threatened Central Europe, and the Fukushima disaster of 2011 have created doubt about the safety of nuclear power plants. Thus, today we'll be discussing the condition monitoring of some major components found in a nuclear power plant. The scheme here shows all the major components of a nuclear power plant. Among this, we will be focusing on the pump motors, water pipes, and the cooling system based on carbon dioxide for the condition monitoring. First would be the vibration analysis of pump motors, in which we will be classifying the signature of vibration in the frequency spectrum, which can be used to determine the cause of a motor malfunction like bearing failure, shaft imbalance, misalignment, or looseness. The second part includes the continuous heat monitoring of the motors to decide whether they are operating above their allowed operation temperature. Third part would be the leak detection of CO2 in the cooling system. For this purpose, a gas sensor would be deployed which would measure the concentration of CO2 inside the containment building and send an alert if a dangerous concentration has been reached. The last part of our architecture consists of the ultrasonic testing of water pipes to detect scaling or cracks inside the pipelines. The vibration sensor is placed on various components of the pump motor in order to detect the high amplitude vibrations effectively. The vibration is then analyzed in the frequency domain to observe a pattern and in turn detect the root cause of a possible malfunction. Considering an idealistic scenario with analysis in terms of harmonic orders, a motor with no defect would provide a single peak at rotational frequency. In the presence of any unbalance, the amplitude at rotational frequency would increase. In case of misalignment shaft, we would see a higher peak at twice the harmonic frequency, and there may or may not be a peak at the third harmonic. And if coupling loosens, multiple peaks would be seen at distinct harmonics. Similarly, if there is a bearing defect, peaks are observed at distinct harmonics of both bass frequencies. Finally, if the resonant frequency of the motor matches with the rotational frequency, we would observe a scenario called resonance. Here we consider a pump motor equipped with a temperature sensor. In a power plant, the pump motor is in operation continuously for 24 hours. Hence, the motor temperature can reach critical values. If we plot the life expectancy of the motor against the temperature, we can see it has a negative slope. For Class A insulation, the permissible temperature is 105 degrees. For Class B, it is 130 degrees, while for Class F, it is 155 degrees. Our system will measure the temperature continuously, and once the temperature goes above the threshold, maintenance department will be notified. As per NEMA, if the motor is operated 10 degrees above permissible temperature, its life reduces to half. The provided sensor used for leakage detection of the coolant CO2 will be positioned inside the isolated containment building of the nuclear power plant. The CO2 concentration will be measured continuously during the regular operation of the power plant. In the case that the cooling pipeline inside the containment experiences a leak, the sensor will detect an increase of concentration and send an alert before any further damage can occur. The leak before break concept is used for this application, which ensures that the leak will develop before a catastrophic rupture can occur. This is a very important aspect which prevents the nuclear power plant from a major disastrous event like a nuclear meltdown. Finally, we see the ultrasonic testing of pipes for detection of scaling and cracks. Here an ultrasonic sensor is moved over the outer surface of the pipe with scaling inside. As the sensor moves along the length of the pipe, three pulses are detected. The time difference between the transmission and scale echo is used to measure the thickness of the scaling at various locations. If it goes above the accepted threshold, maintenance can be planned. The principle of operation for crack detection also remains the same. As the sensor moves over the pipe wall, the echo from the crack is recorded. As the crack has no fixed orientation, the sensor needs to measure the pipe from various angles. The potential outcome of this project consists of creating a classification model for the overall system in order to reduce operation and maintenance costs and increase the life expectancy of the nuclear power plant. The idea is shown here. We try to use a predictive maintenance technique with our sensors to keep the condition of the equipment in a stable state as long as possible to postpone and prevent expensive repairs and replacements. Ideally, the black curve, which illustrates the potential failure of the nuclear power plant, will shift due to the usage of the classification models upwards, which leads to the desired outcome.